Thanks everyone for attending the presentation. I am going to present the paper Deep Learning-Based Hybrid Beamforming for Aerial Massive MIMO-OFDM Systems. My presentation is divided into 5 parts. We first briefly introduce the background of this paper. The Space Air-Ground Sea Integrated Network, SAGSIN, has been widely recognized as a promising architecture to enable the future 6th generation, 6G, communications paradigm shift for seamless global coverage. In SAGSIN, aerial networks consisting of unmanned aerial vehicles, airships, and balloons-based aerial base stations, BS, are key components to support the wide area coverage for scenarios not well covered by conventional terrestrial networks, such as cell edge user service, agricultural monitoring, emergency communication, disaster rescue, remote areas, etc. Communication capacity is crucial for aerial networks to support these application scenarios. To this end, the aerial BS can be equipped with massive multiple input multiple output, MIMO, to substantially improve the system capacity. However, the deployment of massive antenna arrays at the aerial BS leads to the huge dimensions of channel state information, CSI, which bring difficulties to the real-time CSI acquisition and beamforming. Therefore, developing efficient physical layer techniques to meet the SAGSIN's high throughput and low latency requirements is urgent. In time division duplex, TDD, systems, the BS with fully digital array can easily obtain the uplink CSI based on the uplink pilot transmitted by the user equipments, UEs, and then exploits the channel reciprocity to obtain the downlink CSI for beamforming. However, aerial BS, example, airships and balloons, cannot afford fully digital array due to its prohibitive power consumption and hardware cost. Hybrid analog-digital array deployed at the aerial BS can well overcome the above issues. But estimating the high-dimensional channels from a limited number of radio frequency, RF, chains at the aerial BS still suffers from high pilot overhead. Moreover, for frequency division duplex, FDD, systems, the uplink and downlink channels reciprocity does not exist, leading the downlink CSI acquisition more challenging. Specifically, obtaining the downlink CSI in FDD systems relies on the downlink pilot transmitted by the BS, based on which the received pilot signals or the estimated channels are first compressed and quantized at the UEs, and then fed back to the BS for downlink beamforming. Due to the hundreds of antennas at the aerial BS, the resulting high-dimensional downlink CSI matrix would pose a prohibitively high overhead to downlink channel estimation and uplink CSI feedback at the UEs. Additionally, even in the case of perfect downlink CSI at the aerial BS, designing spectrum-efficient multi-user broadband hybrid beamforming is intractable, since the RF analog beamforming part is frequency flat while the practical broadband channels are frequency selective. Therefore, how to achieve accurate CSI at the aerial BS and perform reliable multi-user hybrid beamforming is a critical issue. The next part is system model. This paper investigates the multi-user hybrid beamforming for massive MIMO-OFDM systems, as shown in this figure. We consider the BS is equipped with M antennas and K RF chains. It can simultaneously serve K single antenna users, and the cyclic prefix, CP, OFDM with NC subcarriers is used. Downlink data transmission can be expressed as this equation. As for the channel model, we consider a typical multipath sparse channel model for mmWave massive MIMO-OFDM systems. Besides, we consider that the base station adopts uniform planar array. The next part is the proposed approach in TDD mode. Then, we briefly introduce the processing procedure and problem formulation in TDD Massive MIMO-OFDM Systems. The whole processing procedure can be divided into two stages. The first stage is uplink hybrid pilot transmission. In this stage, all KRF chains are activated for pilot combing. Users send K orthogonal pilots repeatedly over Q time slots. The aerial BS can obtain the downlink CSI based on the received uplink pilot signals. For designing hybrid beamformer, we consider taking some rate as the optimization goal, based on the above processing procedure. The joint design of uplink hybrid pilot combining and broadband multi-user hybrid precoding can be formulated as this. However, this is a complicated joint optimization problem, and how to solve this problem is challenging. We jointly model the uplink pilot combining and downlink hybrid beamforming modules as an end-to-end E2E neural network. The proposed E2E neural network consists of a hybrid pilot network, HPN, and a TDD hybrid beamforming network, TDD-HBFN, at the aerial BS, in the proposed scheme. The CSI is implicitly extracted from the baseband pilot signal through neural networks, which circumvents the difficulty of obtaining high-dimensional explicit CSI under constraints on pilot overhead. The first component of the network is the uplink hybrid pilot network, HPN, in which the pilot combining process of matrix multiplication can be represented by a single-layer fully connected neural network, with the coefficients of the combining matrix serving as the network's weight parameters. To satisfy the constant modulus constraint for the combining matrix, we treat the phase shifter phase values within the matrix as learnable parameters in the neural network, and obtain the pilot combining matrix that meets the constant modulus constraint, i.e., the fully connected weights, through complex exponentiation. In the case of channels exhibiting favorable reciprocity, the base station can extract implicit CSI from the received uplink baseband pilot signal and design a hybrid precoder. As illustrated in the figure, we model this process as a time division duplex hybrid beamforming network, TDD-HBFN. Typical millimeter wave channels exhibit sparsity in both the angular and delay domains, allowing for further compression of the received pilot signal in the delay domain. Therefore, we employ a one-dimensional discrete Fourier transform, DFT, to transform the pilot signal into the delay domain. And the convolutional layers in the neural network efficiently exploit the local correlation of the pilot signal in the delay domain to extract implicit CSI. Initially, the network inputs the delay domain pilot signal into a residual block unit for preliminary feature extraction. Subsequently, the network employs 3 fully connected layers to further extract implicit CSI and concatenates the implicit CSI of individual users into a single entity. The network processes the concatenated implicit CSI through 4 fully connected layers and divides the output into 2 parts. The upper half directly serves as the phase values output for the analog precoding, while the lower half undergoes further feature extraction in the frequency domain through an additional residual block unit, ultimately serving as the output for the digital precoding matrix. As depicted in the figure, each residual block consists of 4 convolutional layers and utilizes residual connections to directly link the input data stream to the output data stream of the 4th layer. The primary purpose of residual connections is to mitigate the vanishing gradient problem, which commonly arises in deep neural networks. To capture the local correlation of the received pilot signal in the delay domain, we set the kernel size of the residual block unit to 1 by 5. We adopt SWOMP-based channel estimation, Lloyd max quantization, spatially sparse hybrid precoding, SSHP, and two-stage hybrid precoding, TSHP, as baseline schemes. The numerical results shows that the proposed scheme can still achieve high sum rate when the pilot overhead is limited. The next part is the proposed approach in FDD mode. Then, we briefly introduce the processing procedure and problem formulation in FDD Massive MIMO-OFDM Systems. The whole processing procedure can be divided into 3 stages. The first stage is downlink hybrid pilot transmission. In this stage, the BS broadcasts Q-pilot OFDM symbols to all users. The second stage is uplink CSI feedback. Each user needs to compress the received pilot signals into B bits and feed them back to the BS. Based on the feedback bits, the BS needs to extract the implicit CSI and perform multi-user hybrid broadband beamforming. We consider taking sum rate as the optimization goal. Based on the above processing procedure, the joint design of downlink pilot signals, uplink CSI feedback, and broadband multi-user hybrid precoding can be formulated as this. We jointly model the downlink pilot transmission, uplink CSI feedback, and downlink hybrid beamforming modules as an E2E neural network. The proposed E2E neural network consists of an HPN at the aerial BS, a pilot feedback network, PFN, at the terrestrial UEs, and an FDD hybrid beamforming network, FDD-HBFN, at the aerial BS. Downlink pilot transmission is modeled as a fully connected layer, which is the same as the HPN in TDD systems. The phase matrix can be learned and determined in the deep learning training stage, and each element represents the phase value of the corresponding element. The proposed pilot feedback network, PFN, skips the explicit channel estimation process and directly compresses the pilot signals into a small number of feedback bits. The gradient of the quantization function is set to 1 for facilitating the backpropagation of the gradient in the training phase. The proposed FDD hybrid beamforming network, FDD-HBFN, skips the explicit channel reconstruction process and outputs the hybrid beamformer directly according to the feedback bits. As shown in these figures, this observation indicates the superior performance of the proposed E2E neural network approach in the case of very low CSI feedback overhead. Besides, we adopt the transfer learning strategy to further fine-tune the E2E neural network in the right figure based on a pre-trained network that assumes the ideal infinite resolution phase shifters. The proposed scheme with the low-resolution PSs can achieve the performance close to that with infinite-resolution PSs, when the resolution of PSs is no less than 3. As for generalizability to different numbers of terrestrial users, since the channels of the different terrestrial users are typically IID, all the terrestrial users can share the same parameters of the PFN, indicating that retraining the PFN is not required even though the number of terrestrial users K changes. As for generalizability to different resolutions of the PSs, with the help of the transfer learning method, we only need to fine-tune the E2E neural network under different B_phase based on a pre-trained network assuming the ideal infinite resolution. The same method can also be used to enhance the generalizability of the network to the different numbers of feedback bits. As for generalizability to different numbers of channel paths, we propose to train the network using samples with different LP to enhance the generalizability of the proposed E2E neural network. As for generalizability to different SNRs, in the case of different SNRs, The anti-noise robustness of the network can be enhanced by using the noisy training samples with different noise power. The last is conclusion. This paper proposes a data-driven deep learning-based E2E approach for aerial multi-user broadband hybrid beamforming. The proposed approach provides a unified framework for both TDD and FDD Aerial Massive MIMO-OFDM Systems for TDD E2E neural network. We jointly optimize the uplink pilot combining and downlink hybrid beamforming, which respectively correspond to the HPN and the TDD HBFN for FDD E2E neural network. We jointly optimize the downlink pilot transmission, uplink CSI feedback, and downlink hybrid beamforming, which correspond to the HPN, the PFN, and the FDD HBFN, respectively. We introduce the transfer learning strategy to adapt the proposed scheme to quantized phase shifters constraint, so that the proposed scheme can mitigate the performance loss resulted from low-resolution phase shifters. Numerical results have verified that the proposed deep learning-based E2E scheme can achieve significantly better performance than traditional schemes, especially in the case of limited channel estimation and feedback overhead. The references are presented as follows. Thanks for your attention.